In this lesson, we'll learn more about some quality control aspects of construction with drilling fluids and about the potential effects of drilling fluids on the engineering behavior of completed drilled shafts. We previously discussed the importance of cleaning the base of the excavation in order to provide good contact for the axial base resistance and also to avoid entrapment of debris into the concrete during trimming placement. Let's look at the clean out and inspection process in a bit more detail. You may have seen this clean out bucket in other lessons. A clean-out bucket is designed to pick up loose debris from the bottom without digging to further advance the excavation. So you see the flat cutting surfaces with no teeth and the trap doors to contain the material and then release it into the spoils container. These clean-out bucket tools can be effective at removing large quantities of debris from the bottom. A clean-out bucket is not effective at removing suspended sediment from within the column of fluid in the hole until enough time has passed for the material to settle to the bottom where it can be excavated with the clean-out bucket. Even after waiting for suspended solids to settle to the bottom, if many passes of a bucket are needed to remove the material, this process may stir things up again. A more effective tool for cleaning the fluid is a pump like the airlift pump you see here, which lifts fluid that is laden with sediment from the base of the excavation, while the hole is replenished with clean fluid at the top. Airlift pumps work by injecting air into the bottom of the fluid-filled pipe. You can see the little airline rubber hose in the background just behind the airlift pipe. And the buoyancy of this air within the pipe begins the circulation process, removing fluid from within the drilled shaft excavation. You can see how the operators here are moving the pipe around the bottom to lift loose debris. A hydraulic pump can also be used for cleaning, with the advantage that the action of the hydraulically operated mechanical pump can be controlled more easily than an airlift. However, the principle is the same. The pump lifts sediment-laden fluid and allows replacement with clean fluid. Sometimes an airlift pump can pump so fast that it is a challenge to keep the hole recharged and avoid losing positive head pressure that is essential to stability. The hydraulic pump can be operated at a speed more compatible with the recharge of the top of the hole. Inspection is an important part of the process in order to confirm that the operation has adequately cleaned the base of the excavation. The first and most common technique is sounding with a weighted tape, as you see in this photo. The criteria for acceptance may vary depending on the application, but generally the sounding is used to confirm that the base feels firm and that there is no soft, mushy material present. This weight has a little foot on it, as might commonly be used for a soil bottom. If the base of the drilled shaft is on rock, the inspector may be looking for a sound thump of the bottom. A short piece of number 18 rebar is commonly used. With a bit of experience, it's pretty obvious whether the base cleaning operation has been successfully completed. A more advanced technique is to use a downhole camera for inspection, such as the mini SID that is shown in these photos. The camera has a housing that is filled with air or nitrogen with water jets to clear the lens and allow the bottom to be observed, as you see in the photo at bottom. The inside of the housing has some gauges that can help to identify the depth or size of any debris on the bottom. This type of inspection may be utilized for large drilled shafts or critical structures where the base resistance is an important part of the design. In my experience, it's a worthwhile technique to use for selected drilled shaft excavations, especially early in the project, to confirm that the cleaning techniques are effective. If sounding using a weighted tape is routinely performed, this technique can also help as a spot check on the inspection process. Here's a mini-SID camera after it's been withdrawn from the hole. So let me ask you, what's wrong with this picture? Obviously, sediment is still settling out of the fluid column and accumulated on top of the camera while it was being used for inspection. Clearly, some more cleaning of the fluid is needed, and this hole is not yet ready for camera inspection. Here's a new device that has just come onto the market. I haven't had direct experience with it, but it clearly represents an effort to better quantify the bottom inspection process, the shaft quantitative inspection device. I took this photo in the Pile Dynamics manufacturing facility. The device is attached to the Kelly bar on the drill rig and then lowered to the base of the drill shaft excavation. Each of the 3 feet has a little pad to stop on soft material and a center probe similar to a cone penetration probe that can be pushed into the bottom. The plastic bucket of sand on the floor represents a soft spot in this test of the device. And the probe identifies it by the difference in elevation between the pad and the center probe. The penetration resistance of the center probe can also provide information related to the strength of the bearing material, at least within a few inches of the bearing surface. This photo shows the base of a 6-foot diameter drilled shaft constructed under slurry that was exhumed as part of a research project into drilled shaft concrete. The lowermost piece of the concrete was cut using a wire saw and then stood upside down so that the top of the concrete you see here provides a casting in concrete of the bottom of the drilled shaft excavation. The pattern on the concrete represents the impression left by the cleanout bucket on the bottom of the hole after cleaning. To anyone who doubts that the base of a drilled shaft constructed with slurry can be cleaned, this photo is pretty compelling evidence that it can be, using the correct equipment and techniques. This photo sampling and testing the drilling fluid helps to ensure that the characteristics of the fluid are within generally accepted guidelines and project specifications. This operation is most important prior to concrete placement, but it is also important that the slurry properties be appropriate for maintaining stability during excavation. The slurry may be sampled throughout the fluid column, although the bottom is the critical place for testing prior to concrete placement because that's where it's likely to be the dirtiest. This photo shows a device for capturing a slurry sample at depth. For stability and to avoid fluid loss during excavation, the most important property is probably the viscosity. We don't measure viscosity directly, but rather use a simple standardized test to provide a measurement that reflects the fluid viscosity. The Marsh funnel is a standard size funnel with an opening of a certain size, and you can see the inspector measuring the time required for a certain volume to pass. The more viscous the fluid, the longer this will take. Water takes about 26 seconds for a quart to pass, so a typical time for drilling mud is in the 30 to 45 second range. Many project specifications allow 28 to 50 seconds, but that can depend on the applications. Higher viscosity would be even better for stability of the excavation, but the filter cake could be so thick as to be detrimental to the side resistance. Polymers are often used with a higher viscosity, partly because the lack of filter cake may require higher viscosity to limit fluid loss, and partly because the lack of a filter cake eliminates the concern about the thickness. Another simple test is the mud balance to measure the unit weight of the fluid. This device and scale is calibrated to indicate unit weight for a specific volume of fluid held in the little cup on the right. Bentonite which is too heavy is likely too contaminated with soils for concrete placement, even though a heavy slurry may be beneficial for stability. Unit weight is not normally an issue for polymer, which does not typically hold a lot of material in suspension. The sand content measurement gives a direct measure of the suspended particles, at least those that will not pass a number 200 sieve. The upper limits shown are prior to concrete placement, and one would not normally worry about sand content during excavation. Also, these limits are typical guidelines that are incorporated into project specifications. In reality, it may be necessary to reduce the sand content well below these limits for large diameter drilled shafts that are quite deep. Think about why for a minute. Concrete placement in a 3-foot diameter shaft that is 40 foot deep may only take 15 or 20 minutes, and so there's not much time for any sand in suspension to settle out. Concrete placement in an 8-foot diameter shaft that is 150 feet deep may take several hours, allowing a lot more time for suspended solids to settle out during concrete placement. This photo illustrates the risks with slurry that has too much suspended sediment. If sand settles onto the rising column of concrete during placement, the concrete may fold it in. These sand pockets are often identified in integrity test measurements and represent imperfections in the hardened concrete. Small imperfections in the concrete are probably not a big deal, but a lot of time and money can be expended trying to identify the magnitude of the problem, and anyway, these issues can be avoided with good practices. We'll learn a lot more about concrete for drilled shaft construction in another lesson. The pH is important for the bentonite or polymer to work properly, so this is normally checked at the beginning with the makeup water. The chemical reactions which cause polymers to form are pretty sensitive to the pH, so this is particularly important for polymers. In this photo you can see the soda ash which is being used to adjust the pH, generally speaking to increase it. So let's talk for a few minutes about the potential influence of drilling fluids on the axial resistance of a completed drilled shaft. We need to start by acknowledging that the most important influence is a positive one. By keeping a stable hole and maintaining the integrity of the bearing materials, this excavation obviously needed some support. And if there is seepage into a hole, even with casing, then debris can flow into the excavation and be deposited onto the bottom. Uncontrolled seepage into the hole is also detrimental to concrete quality, as we have discussed previously. In my experience, it is actually easier to clean the bottom of a drilled shaft under fluid using the techniques we discussed earlier than it is to clean a, quote, dry excavation. Use of proper drilling fluid with good base cleaning operations can avoid the soft toe effect that is evident in the load test results presented in this plot. This little ducktail at the beginning indicates that the bottom didn't provide much resistance at first, and then it became stiffer after about a half an inch of displacement. The bottom debris didn't mean that the base resistance was not present, but it took a larger displacement to mobilize it. These data are from an actual load test of a drilled shaft in soft Florida limestone. The plots of 2 load tests show the behavior of 2 drilled shafts on rock at a site near Atlanta with a clean base. The high base resistance is mobilized at very small displacements. Test shaft 1 is on weathered rock and test shaft 2 is on hard rock, but both of these exhibit very stiff initial resistance. We have alluded to the fact that we don't really want an excessive buildup of bentonite filter cake at the borehole wall because it could be detrimental to side resistance. There is increasing evidence that the unit side resistance of drilled shafts constructed in granular soil using polymer drilling fluids is superior to that of drilled shafts constructed using bentonite, even with accepted practices. This plot shows data from one of the earlier full-scale comparison studies, and there have subsequently been more showing similar evidence. This effect would not be expected and has not been observed in low permeability cohesive soils, likely because the lack of fluid loss does not result in a filter cake deposit at the borehole wall. It is also of interest to note that the side resistance in either case appears to be mobilized at small displacements, but exhibits ductile behavior out to nearly 2 inches of displacement. It's reassuring to note that the side resistance doesn't typically drop away in a brittle manner. This subject will be discussed further in the design lessons. Another potential benefit with polymer slurry materials has been identified in recent years, and that is the tendency of the polymer to reduce the amount of wetting and degradation of shales at the borehole wall. Many geotechnical engineers have experience with the rapid degradation of shale exposures in road cuts, and the same thing can happen in a drilled shaft excavation. The result of degradable shale could be that the side resistance of a rock socket into such material would be affected by the degraded shale rather than the stronger intact material. The results of these slate durability tests suggest that the polymers can reduce the tendency of some shales to degrade quickly in the presence of water. Anecdotal evidence from several load tests on projects in these materials support the notion that polymers can be beneficial in preserving the integrity of shale bedrock bearing materials. So, to summarize our series of lessons on drilling fluids, we note that this technique is an important part of drilled shaft construction, and that designers need to be familiar with the use of fluids in construction. The most important issue is that a positive head pressure be maintained at all times so that the stabilizing effect of the drilling fluid is maintained. Finally, we've described the many quality control issues needed to ensure good foundation performance. Thank you for listening.